So last time we briefly talked about ideal gas law, I think, and I was saying at the end that for all of these other simple gas laws, let me just go to Avogadro's. In all of these, we have V1, we have V2, we have N1, we have N2, we have a change in one condition, and we can predict what the change is going to be in the other condition, whether it's number of moles, volume, temperature, or pressure. And so the combined gas law was like combining those. I actually don't think we had it in a slide. But the combined gas law was the, P1 V1 over T1 equals P2 V2 over T2. And you can actually even take this one step farther and we could put N in there. So it could be N1, N2. And when you get to this point and you can put all of these gas laws together, that's when you get the ideal gas law. Because, and this is something that I haven't done yet, but I think it'd be interesting to take a whole bunch of different gases under different conditions. As long as they're ideal gases, pressure times volume divided by the number of moles divided by the temperature in Kelvin always gives you this value of R. So for any ideal gas, as long as it's behaving ideally, it'll always give you this 0.08206 liters atmospheres per mole Kelvin. And these units here in that R value, L is volume, atmospheres is pressure, moles is N, temperature in Kelvin is T. And that's basically that combined gas law if we include number of moles. So the reason that this is handy is that when we write the equation out as one line, we can then, for any ideal gas, as long as we know three of these, we can calculate the fourth. So if I know the volume, I know the pressure, I know the number of moles, I can calculate the temperature that ideal gas is. Or if I know the pressure, I know the number of moles, and I know the temperature, I can calculate the volume. It's no longer just dependent on knowing what it was before, changing something, and then knowing how that change affects another parameter. And this is one of those things that falls out of chemistry. The whole world and everything is so chaotic. Why do all ideal gases behave this way? And I think this is one of the things that drove people to think about things like kinetic molecular theory. If all ideal gases behave the same way, then there must be some underlying set of principles that applies to every gas. So we'll talk again more about kinetic molecular theory in a bit. But here we got a nice little diagram. Hard to tell which of these are red. Some of these are red. Let me try and highlight them. Like here, those are red. These. We can get Boyle's law, Charles' law, and Avogadro's law. There's definitely somebody on the roof. So the screen's shaking. Yeah. That'd be crazy. So if we make any of these constant, these are the ones in red that are constant. R is always the same value, depending on you're using the same units. Temperature and pressure are being held constant here, so it gives us a relationship between just volume and number of moles, which are directly proportional. That's what this little fish means, little fishy symbol. If we make number of moles and pressure constant, that's the relationship between volume and temperature, so they're proportional. And then volume and pressure are inversely proportional. And basically, you've already done some problems with these. In the simplest form, it's just plugging all of the right numbers into the right spots. And maybe the one real key to that is questions aren't always going to tell you, oh, this number is the volume in liters. This number is the number of moles in moles, or the mass in grams, that kind of thing. So you need to know the units that represent those. So we got 8.5 liters here. And we know this is an ideal gas law. So if we write out like all of our possible variables for an ideal gas law problem, volume is going to be 8.50 liters. Pressure is, all right, what is the pressure? So we need to find the pressure, and it wants it in atmospheres and PSI. We have a number of moles. R is always the same thing, as long as it's in these units. Also, I tend to write atmosphere liters per mole Kelvin. It makes more sense. I don't know. That's the order in my head. The order of atmospheres and liters doesn't matter, though. And then just 1 second, let me write temperature in. 305 Kelvin. You got a question? Yeah. Now this question asks, what is the pressure? So we're looking for the pressure, and we've basically written out all of the numbers that we do have, and we can just plug those in. Pressure times the volume, 0.552 moles, 0.8206, atmospheres, liters, mole, Kelvin, 305 Kelvin. One of the other nice things about these problems, because we don't have very many constants that go in aside from like R in this case. So all of the units will always work out to cancel out and give you whatever units you're looking for in your answer. So 0.552 times 0.08206 times 305. And then so I basically multiplied all of these together, and then we divide both sides by 8.50 liters. Oh, I missed a zero. Sorry, 1.63 atmospheres. Does anybody know how many psi per atmosphere? It's not 1-to-1. It's 14.7. 14.7 psi for every 1 atmosphere. Oops, not that. This. So multiply by 14.7. It's not ATM. PSI.
There on the R constant, why did we put the atmosphere times the big input?
Those are the units of the constant.
Okay, so
we say
writing those all the time?
Probably. Should be writing those in. And like here, I'm multiplying moles by this is 1/moles. So basically moles divided by moles, that cancels out. Kelvin divided by Kelvin, that cancels out. And then when I divide both sides by liters, I've got liters on top here. So now it's liters divided by liters. That cancels out. So all of the units should cancel out to give you whatever unit you're looking for. Atmospheres in this case. Yeah. Oh, I didn't use the rounded. I didn't actually use 1.63. I used 1.62536, so on and so forth. So it comes out a little bit lower. And you should not be rounding in between those calculations. Okay. Ideal gas law. Got another one. The other nice thing about if you're always writing down the units for R, the units for R tell you which units you need everything else to be in for that equation. So if I write down R first on this one, that's atmospheres, liters, moles, Kelvin. So I got to have pressure in atmospheres, volume in liters. Moles is always going to be in moles. Temperature needs to be in Kelvin. So when I look at a problem like this, I say, it says what volume does 0.556 moles of a gas occupy at a pressure of 715 millimeters of mercury at a temperature of 58 degrees Celsius. So I can compare these units. So for pressure in millimeters of mercury, for temperature degrees C, does that match R? No. So we need to convert those so they do match R. So 715 millimeters of mercury. Does anybody know that conversion? 760. It's 1 atmosphere. Huh? Oh, 715 divided by 760, that's going to be 0.940789. I'm writing out too many decimals here because we want to have those extra decimals when we do the rest of the problem. so we don't get rounding errors. But what else do I need to convert? Celsius into Kelvin. So we add 273.15. That's 331.15 Kelvin. And now we can do PV equals nRT. It's going to be this. Volume is what we're looking for. Of course, every time. I put that over there and I was like, that's a little close to the edge. Uh, 33115.556. And that and this. And then divide by. So the volume equals 16.1. Okay. Good. I'll give you any pressure conversions that you need. Yeah.
The 58 degrees Celsius is 260.
When we added 273.15, this has 0 decimal places, and since it's addition, smallest number of decimal places means that this is 3 sig figs.
Yeah, converting to same things basically this one.
Yeah, but it basically ends up being based on the decimal places of the first number. So if it had just been 8 degrees C, it still would have been 3 sig figs after this.
So we would use a temperature, not like the sig fig from the walls of that.
Yeah. So you got to look at how this number, how we convert it. Because this is, I guess this might be exact. But then it's the number of decimal places when you add.
But then there's a total, right? The 331.
No. This would just be 3 sig figs. Because there's no decimals on 58. We keep the whole thing because we don't want to get rounding error. But no decimal places would just be at the 1. Okay. All right, briefly talked about this. This is just for those Alex problems, the ideal equation of state problems. So if you either didn't get through those in the last week's module, you go back and do them. The key here though, and I think we did one example. Oh no, I didn't even go over one example. You can convert all the numbers and use atmospheres, liters per mole Kelvin for everything. You can convert the pressure from, some of the questions were in pascals, some were in megapascals. You can convert it from megapascals into atmospheres. Not a problem. And you can convert meters cubed into liters. Also not a problem. I think that these problems were set up though to make you use this, because then if you use meters cubed pascals per Kelvin mole, then you don't need to do those extra conversions. And it's just 1 step faster, 2 steps faster. So that was last week, so we're going to skip over that. Okay, one of the most useful things about ideal gases is this idea of standard temperature and pressure and molar volume. So standard pressure is always 1 atmosphere, 760 torr, and the standard temperature is 273 Kelvin or 0 degrees C. Actually, that should be 273.15 Kelvin, 0 degrees C. It's useful for making comparisons between gases because I can take any gas and using like the combined gas law or using the combined gas law, I can convert it into standard temperature and pressure and figure out what the volume would be, what the volume would be at STP. And then the molar volume is the volume occupied by 1 mole at STP. Again, standard temperature and pressure. So it's 1 mole. And it's a very similar idea to molar mass, right? The molar mass is the mass of 1 mole in grams. This is just the volume of 1 mole. So we can plug all of those in. Our pressure is 1 atmosphere. Our volume is what we're going to be finding in liters. N is 1 mole. T is 273.15 Kelvin. All right, and R is 0.08206. So this ends up being, P V equals N R T. I'm going to arrange it ahead of time this time. N R T over P. So it's 1 mole times 0.08206 times 273.15 divided by 1 atmosphere. So 0.08206 times 273.15. And the molar volume is 22.41 liters. So remember, we're talking ideal gases. This is any gas. So for literally any gas, as long as it's at generally low pressure, high temperatures, low pressure and high temperatures, it'll act ideally or very close to. It will have 1 mole of that gas will have a volume of 22.41 liters. Doesn't matter what it is. Could be oxygen, could be xenon, could be fluorine. Better hope it's not fluorine. Fluorine is scary. Low pressure, high temperature. And we'll talk about why low pressure and high temperature. Gas, 22.4, 22.41, 6.022 times 10 to the 23 molecules of gas. Again, doesn't matter the identity of the gas, it'll take up that amount of space. Now, the way that the gases are different is that 1 mole of different gases will have different masses. So it's 1 mole of O2, for example, that's going to have a mass of 32 grams. If it's hydrogen, 1 mole of H2, it's going to be about 2.02 grams. So the volume that the gas takes up is the same. But again, because the gas particles are heavier or lighter depending on the identity of the gas, they're going to weigh more or have more mass depending on the identity of the gas. And actually, if I can write it like this, so like 1 mole of O2 would have a volume of 22.41 liters. 1 mole of H2 would have a volume of 22.41 liters. So what's mass per volume? That's moles per volume of solution. Molarity is moles per volume of solution, but grams per liter, grams per milliliter? No, we could convert the grams into moles, but this is already for 1 mole, right? But I'm saying for 1 mole of hydrogen, for 1 mole of hydrogen is 2.02 grams, 22.41 liters. That's the density of that gas. And we can use gas laws to calculate the density of gases. And we could also use that to find, if we know the volume, temperature, pressure, then we can find the number of moles, and we can find the molar mass of the gas if we know what its density is. So like here, some other ones, helium, 22.4, they're all 22.4 liters. They would have different masses though, depending on their molar mass. So 1 mole of helium would be about 4 grams. 1 mole of xenon's heavy. Is big. Xenon is 131, so it's about 131 grams. And then methane would be about 16.05 grams. So same volume for all of them, but different masses, depending on how heavy or massive the atoms are. So this is taking that idea, but giving masses of some gases Which one would have the greatest volume at STP? So we're given 1 gram. If I had 1 mole, then it should all be the same, right? Because 1 mole of each, then would be the same volume. It's like for hydrogen, right? Really what we need to know here is how many moles are there, because these gases weigh different things, have different masses. So 1 gram of hydrogen, how many moles of hydrogen is that? It's H2. So it's about 1/2, because I would essentially divide this by 2.02 grams per 1 mole. So equals about 0.5. So would oxygen be more or less moles? What's the molar mass of oxygen? O2. 32 per 1 mole. So basically I end up taking the 1 gram and dividing it by 32, and now instead of 1/2 of a mole, I have about 1 divided by 32, 1/32 of a mole of O2. So is that going to take up more or less space? It's going to be a smaller volume. Yeah. Whatever 1 divided by 32 is. So the greatest volume, because argon is molar mass of 39. Yeah, so hydrogen's going to have the largest volume. And what would be the smallest volume? Argon would be the smallest then, because I'd be taking 1 gram dividing by basically 40. And that's a smaller number than 1 divided by 32. I mean, you get your calculator and actually type it in. It'll tell you the number of moles. And it tells you that it's at STP, so you could actually calculate the volume of each of these gases at STP. But you can save some time by just getting approximate numbers for the moles. What is STP, by the way? Standard temperature and pressure. Standard temperature is? Yeah, 0 degrees C, 273.15 Kelvin. Standard pressure is? Standard pressure? 1 atmosphere. Just remember that. Very easy, because it seems like a simple enough thing, but it's one of those things when you get to a test that you just end up forgetting. You might see the STP, but just not think about it. Whenever you see STP on a question, you should write that out. 0 degrees C, at the very least, write out 0 degrees C, 1 atmosphere. If they have the same mass. So here we've got 1 gram of each, right? If I had different masses of each, if I made this, say if I made it 2.02 grams of H2, and then 32 grams of O2, and 40 grams of argon, now which one has a greater volume? Nope, it's just all the same. Now, technically, I wrote 40 for argon, and argon's molar mass is a little bit less, so 40 is a little bit more than 1 mole. I wouldn't write it that way on a test, it's just writing it, rather than write out the whole number. But yeah, so it depends on the mass. If you've got the same mass of every gas, you need to know how many moles. Yes, more moles does always equal greater volume at the same temperature and pressure. Okay. Like I said, not going to spend too much time on density of a gas at STP. But the only thing we need to calculate density is the mass and the volume. It's usually mass and the volume in grams per milliliter. For gases, grams per liter. Just got to specify which units you're using. If we take actually molar mass and divide it by molar volume. So molar mass has units of what? Grams per mole. So if I do grams per mole and then divide that by molar volume, which is the liters per mole. Now this is one of those things when you take a fraction and you divide it by a fraction, it looks weird. So you can rewrite this as grams per mole. This is what I used to always do. And then you multiply by the other one flipped. So I take this one and I flip it. I put it over here. So moles over liters. And would you look at that? Moles cancels out and gives you grams per liter. So if you knew the molar mass and you knew the molar volume, you can calculate the density. And there's an equation on this next slide. I think you guys know how I feel about equations. Because ultimately you should be thinking, oh, if I need to calculate the density of a gas, I need to find the mass, I need to find the moles. You can derive an equation from PV equals nRT. So it becomes density equals the pressure times the molar mass divided by R divided by T. And I'll write this out just real quickly. The way you do it is you take the fact that density equals mass divided by volume, and you rearrange that to say volume equals mass divided by density. Then you take PV equals nRT, and you substitute in mass divided by density. Oops. So P times now mass divided by density equals nRT. And then since I want to solve this for density, I'm going to multiply density over to the other side. Basically multiply both sides by density. So this becomes pressure times mass equals nRT times D. And then you divide both sides by nRT. And then I get pressure over RT, and I get mass divided by moles, grams per mole. So mass divided by number of moles becomes molar mass. So pressure times the molar mass divided by RT equals the density. So unless I'm just showing you that to show you how you get there, unless that is super clear in your head, you would just have to remember this equation. Or just calculate the number of moles, or calculate the number of moles. Use that to find the grams, calculate the volume, and then you can find the molar mass, or the density. Okay. Let's do one of these. Which one's harder? They're about the same. Let's do the first one. So calculate the density of xenon gas at a pressure of 742 millimeters of mercury and a temperature of 45 degrees C. So R 0.08206 atmospheres liters per mole Kelvin. So we got to convert millimeters of mercury by dividing by 760 to get atmospheres. So 0.976315. Something around there. And then 45 plus 273.15. 318.15 Kelvin. Okay, so what do I need to know about this to be able to calculate density? I need the mass and the volume, because our density is going to be mass divided by volume, or grams divided by liters when we're talking about gases. Yeah, so there's two ways we can do this. One is we could use that equation, that's density equals pressure times the molar mass divided by RT. Plug the numbers in and solve it. I trust that you guys can plug the numbers in. We can look at the molar mass of xenon. It's 131.29. So you can plug all those numbers in and solve it that way. But what if I can't remember what that equation is? How do I solve it then? This is another one of those, just assume an amount of something. Oh, the 22.4 moles per liter? That's only at STP. I was thinking of a different way of doing it, but you could convert the temperature, or you could convert to STP and then use the 22.4 and this molar mass. The thing was, I was thinking is, what are we missing in this? We want to find volume, but we're missing a number of moles. Yeah, so what we do is we assume 1 mole. Because if I have 1 mole of xenon, then I know its mass. 1 mole of xenon is 131.29 grams. And then I can calculate the mass or the volume of 1 mole, because I'll plug in 0.976315. And then 1 mole times R times the temperature. Because remember, as long as I have 3 of the 4 different values for a gas, I can calculate the last one. And it doesn't matter if this is 1 mole or if it's 10 moles. It gets a little bit ridiculous if you start picking like crazy big or crazy small numbers, but 1 mole is reasonable. And so now I can solve this for volume. That times that divided by, so this is 26.7407 liters. And I'm not rounding yet because we're not done yet. So what mass of xenon gas do I have? Yeah, because we said 1 mole. So if I have 1 mole of xenon gas, then it's 131.29 grams. So if I want grams per liter, 131.29 grams divided by my 26.7407 liters, that equals 4.91 grams per liter. 2 ways you can do it. Remember the equation, density equals pressure times molar mass divided by RT, or use PV equals nRT. Can't really think of a situation where you wouldn't just use 1 mole, because then the molar mass is the same. You just use the molar mass, use 1 mole, solve for volume. Yeah. And like I said, let's do this one at least. So arrange the following gases in order of increasing density at STP. So it'll help here to have density as grams per liter.
I left it at home thinking I was going to need it today.
I could have needed it.
The one that would help me with this is at home on my desk. Very upsetting.
That's okay, it's just an in-class question. So arrange the following gases in order of increasing density at STP. I think there's an assumption here that's implied that we have the same number of moles of each type of gas. Although, technically, if we had more moles or less moles, it would take up larger volume. So density stays the same. But it's a little bit easier to think about it if we think about them being the same number of moles. So what's going to have the highest density? Whatever weighs the most. So if we assume 1 mole, because remember STP, 1 mole of gas will have the same volume. So we're comparing the same things. So you say if I have 1 mole of oxygen, how much would 1 mole of oxygen weigh in grams? About 32 grams, O2. What about F2? Do you need a periodic table?
Yeah, it's about.
Sounds right. About 19 is fluorine. That's one fluorine though. So F2 would be about double that. So 38. And then Cl2 is another one. So Cl2 is about 70. And what about neon? Just one neon. Yeah, that you got to watch out for that on these problems. All of the molecular elements are going to be heavier than their periodic tables, than the periodic table is going to say, because it's two of them. Neon was 20. Okay. So now we've got those written down. Now again, I said, let's just assume 1 mole. The amount doesn't actually matter. Density is independent of how much of it you have, but it's easier to compare them if we're talking about the same amount. So what's the volume of all of these going to be? They're all going to be 22.4 liters. So I'll have 32 divided by 22.4. I'll have 38 divided by 22.4. I'll have 70. And again, when you're doing these kinds of things where it's just sort these, it doesn't have to be super exact. Question? That is the volume of any gas, ideal gas, at STP. Yes, that is something to memorize. That is something to be looking out for on any gas law problem, because it can make your life a lot easier. Okay, so which one's going to have the highest density? Cl2, right? It's the heaviest. And since I'm dividing them all by the same thing, the only thing that matters is how much more massive they are, or whatever is the higher mass. So Cl2 is going to be the heaviest, or the most dense. So we can cross out this last one because Cl2 is not the first one. And what's going to come after Cl2? Chlorine. Fluorine. Yeah, because fluorine is the 38 divided by 22.4. Chlorine's 32, or sorry, oxygen's 32. So fluorine's going to be the next, followed by oxygen, and then neon's last. I think there is an Alex question like this. Density of gases. Yeah. Okay. This is the lab, the second lab this week. It's molar mass of a gas. So molar mass of an unknown volatile liquid can also be determined experimentally. This is a lab that I do in Chem 20, where you take a volatile liquid, you put it into an Erlenmeyer flask, and then you put a piece of foil with a little hole on top. And then you heat it up. All of the liquid turns into a gas and should displace all of the other gases that are in the flask. Then, when you turn the heat off and you cool it down, the liquid recondenses. The liquid that condenses is all of your unknown liquid that was filling the flask. So from that, you can determine what the molar mass is, because you can just weigh the liquid, that's the mass, and then you use gas laws to figure out what the number of moles is. So you got to record the temperature, the pressure in the room, and then the volume of your flask. And again, on things like this, like density, molar mass, molar volume, it really all just comes down to remembering what units make up that larger unit, right? Molar mass is a compound unit of mass and moles. Molar volume is liters and moles. Density is grams per liter. If you can remember those units that go into it, that's what you need to find that value. So I just need to find the mass in the moles to find the molar mass. All right, so real quickly, sample of a gas has a mass of 827 milligrams. And again, we've got volume, we've got temperature, we've got pressure. So that means we can calculate the number of moles. We do have to do some converting. So millimeters of mercury divided by 760. And then 88 plus 270.15 So temperature is going to be 361.15 Kelvin. And you can always rearrange the gas law equation before, whoops, you plug numbers in. So this time I want to find N. 1.282894 ATM times liters divided by R and temperature. So 0.116878 moles. But we want to find molar mass. And it's given away, but what are the units of molar mass? Mass over moles. Mass normally in grams, so we've been given milligrams. So that'll be 800, or sorry, not 800, 0.827 grams divided by my number of moles. 70 point, and I guess I rounded just enough because this comes out to 70.8. $70.7. Any guesses as to what the identity of the liquid is? It's not one that you would want to be doing this in a Gen Chem lab. Huh? Oh, I guess it could be radium. Maybe. Although radium is a solid. Where's radium? Wait. No, germanium is like the closer mass per moles, but it's a diatomic gas. It's chlorine, probably chlorine gas. But yeah, you don't want to be playing with that. It might be something else. It could be a organic compound of some kind. Any questions? Nope. Okay. So you might be given, now you have to be given the mass, I think, or given some data about the mass to be able to calculate that without calculating. Like maybe you're given the density. That's the conversion for millimeters of mercury. 1 atmosphere is 760 millimeters of mercury. Do you have a question? I know, I'm being very lazy about units today. I really want to talk about the other stuff in this chapter. Might tell you something about what's on the exam. All right. Don't have time to talk about mixtures of gases. Mixtures of gases might seem a little bit confusing at first, a little bit complicated, but it's actually pretty simple. Because again, the volume of our gases doesn't depend on the identity of any of the gases. Doesn't matter what it is. The only thing that matters is how many moles of that gas is present. So if I put in, I guess, the air that we're breathing right now, or similar air, this is a dry air mixture, so there's no water or anything in it, but it's mostly nitrogen, then oxygen, argon, carbon dioxide. And if we were at sea level, the entire 1 atmosphere would be made up of these percentage of moles of those gases. Because again, identity of the gas doesn't matter. I can make 1 atmosphere of a gas that could be 50% nitrogen, 50% oxygen. Wouldn't change anything about that ideal gas. I could have any number of different types of gases altogether. As long as we're still at a reasonable temperature and pressure, it'll act like an ideal gas. So in most of what we've been doing already, basically we've been saying we have one type of gas. Haven't specified what it was because it doesn't actually matter. And so even things like air, we can treat all of the air together as one type of gas, and it'll follow the ideal gas laws. You can, though, have different mixtures of gases. So the first thing we're going to talk about is Dalton's law of partial pressures, which basically says that the pressure of a total gas is the added partial pressures of each of the gases that make up the mix. Every component of the mixture is contributing some amount of pressure to the total. And so we call the pressure due to any single gas would be P sub n, and we could replace the n with the formula for that gas. So I might say something like the pressure total, TOT, total, tote, of, for example, the air in this room would be the pressure of nitrogen plus pressure of oxygen plus pressure of argon plus the pressure of CO2, and then so on, because there might be more and more gases, every one being a smaller and smaller piece. So if I had, again, if we were at sea level, if we assumed 1 atmosphere, and actually yesterday I looked up the pressure for the day and it was like exactly 1 atmosphere. Kind of weird. So if I say that the pressure total is 1 atmosphere, and then we come back up here and say, oh, 78% of the air is nitrogen, 21% of the air is oxygen, 0.9 is argon, 0.04 is carbon dioxide. That is the amount of the total that each of those will contribute. So nitrogen will be contributing 0. Gosh darn it. Short-term memory, man. 0.78 atmospheres. Oxygen will be contributing 0.21 atmospheres. Argon will be contributing 0.49. And then carbon dioxide will be contributing 0.04. And that probably doesn't add up completely to 1. But again, whatever partial gases, there's also other things in the mix. And you could also think of this from a kinetic molecular theory point of view. That's the amount of force that those particles are contributing to colliding with the walls. The air is mostly, the air that we're breathing is mostly nitrogen. So most of the collisions are from the nitrogen molecules, N2. And then about 1/3 of that is from oxygen. And then less than, or sorry, not 0.9, 0.009, 0.0004. Much smaller. They're all divided by 100. So whatever the percent is, divided by 100 is the proportion. All right, so most of the atoms from the air that are colliding with you are nitrogen. That's all there is to partial pressures. The way we can use that, I guess this is to say that the total pressure, if we were to say the pressure of A is the number of moles of A, and then if it's all in the same container, the R is always the same. Temperature and volume is going to be the same. So the pressure contributed by our gas A would be, this is the gas pressure from gas B, from gas C. And then we could say they're all being multiplied by RT, so we can just factor that out. So if I took the number of moles and added those all together, that would give me, and then multiplied it by RT divided by V, that would give me the total pressure. Or we could say all of the gases added together. So you could rearrange this equation to figure out one of the partial pressures. It's a lot easier to measure the total pressure, and then maybe you run some reaction and it creates some other gases, and you want to know what the pressure is of something unknown. You could calculate that with this. And actually, that's one of the things we do with water the most. So mole fraction is really just another way to look at the same thing. And that's what I did with the percentages of the composition of air. I took the fraction of the air that is made up of nitrogen, and I said that's the mole fraction of nitrogen. It's making up that fraction of the total amount of air. And again, this, you can rearrange PV equals nRT to get this relationship. But the mole fraction is the number of moles of one part of your gas divided by the total number of moles. It's like calculating a percentage, except you don't multiply by 100. And then if you want to find the pressure of that gas or the pressure contributed by that one type of gas, it's the mole fraction times the total pressure. Like the same saying, what is 70% of all of the pressure, or 78% of the pressure is nitrogen. If the total pressure is 1 atmosphere, then it's 0.78. Again, for gases, we're just taking the pressure of nitrogen in regular air. This is the mole fraction of nitrogen. It's 78% of the air. So divide that by 100, we get 0.78. If the pressure outside is 1 atmosphere, then 0.78 atmospheres is what we're getting from nitrogen. So if you could magically disappear all of the nitrogen with a Thanos snap, as dated as that reference is becoming, you could snap away all the nitrogen, all of a sudden there would be 0.78 fewer atmospheres of pressure. We would all experience violent decompression. This equation I think is most useful for, I should have an example of it. If you ask the opposite question, so if I say that the pressure of nitrogen, 0.78 atmospheres of N2, its mole fraction is 0.78, oops, N2, mole fraction N2 equals 0.78. And that's unitless because it's a fraction. What is the total pressure? Because at least in my mind, going backwards like this with percentages or fractions, just, I don't know, never completely clicks. So I always write this one out. But if I write out that my pressure of nitrogen equals the mole fraction of nitrogen times the pressure total, now I can plug those numbers in. The pressure of nitrogen is 0.78 atmospheres. And if the mole fraction is 0.78, divide both sides by 0.78, and this will become 1 atmosphere equals the pressure total. Obviously here, I think it feels a little bit weird because this is the mole fraction and the atmospheres are the same number. That won't always be the case. This is the kind of calculation that you have to do if you go diving, because you need the pressure, the mole fraction of oxygen needs to be 0.21. The atmospheres of pressure, 0.21 atmospheres of oxygen. And if you keep increasing the pressure, then the pressure of oxygen keeps increasing. But if the pressure of oxygen gets too high, you can get oxygen toxicity. And so you need a smaller and smaller fraction of oxygen. All right, that's 7:20. We'll get through the rest of the important stuff on Wednesday.